Hi folks, welcome. I'm Jim Hanmer. I'm a Principal Solution Architect at AWS, and my role is generally working with startups, so companies like that haven't been founded that long and usually quite small, right through up to scale-ups. In terms of my background, I started out as a software engineer. I've done quite a few different jobs over the last few years, but about 10 years in startups as well. So I've been CTO in a few startups as well as doing a lot of the engineering. And now, I just kind of like the role where I go around and talk to lots of startups and find out what they're doing and help them make the most about technology. So in terms of tonight, what we're going to talk about, the behind the curtain aspect is really, you all probably know a bit about AWS, right? But maybe you don't see what goes on in the back room, right? So it's really about bringing some of the lessons that we've learned over the years of running massive cloud infrastructure, and thinking about how you can apply that to your own environments, whatever it is that you're doing. But to get things started, what I thought I'd do is we can do a quick survey. So you can either, if you want to grab that QR code, I think it's on the next page. Let's have a look. Yeah, you should be able to get it from there. So if you sign up on that, you should be able to answer, and we should get a result in a sec. So basically, what describes your use of AWS? If you have never heard of it or are you using it a lot, just to give me a sort of bit of context of where to pitch this. Cool. Okay. Yeah, it's a good mix. But okay, so you know what it is. That's a good start. Okay. See if this works with the clicker. That'll be magic. I'll give a couple of minutes for everyone to respond. Nice. Okay, so pretty cloud friendly. A couple of people maybe got something to learn tonight. Okay. As DevOps folks, I guess you have to deal with outages. When was the last time you dealt with an outage? Hopefully not now, but you never know. Yeah, good mix. Really? Okay. I'm sorry. Yeah. Okay. So some of this will definitely be relevant to you then, because you're the people who deal with this kind of thing. That's good. Okay. I'll jump on to the next question. Sorry, I'll go through it quick because we've got the time. Okay. So I'm assuming you've got a database. You might not have, but if you haven't, just improvise. What happens if your primary database goes down? Yeah, okay. Some people are being honest. Few minutes, few hours, automatic failover, very good. I'm glad to see it. Yeah, nice. Okay, so a mix, but definitely some sophistication in the DevOps practices here, which is good to see. Okay, and then last one, how do you deploy to production on a Friday? Yeah, same as any other day. That's the good answer. I'd say either don't do it ever, or if you're really confident and you've got a good CI/CD pipeline, then Friday's just another day, right? Yeah, or you want to sucker somebody who's on call into doing it. Yeah, okay, cool. Let's go back to the slides then. So, what we're going to talk about. A little bit about some of the challenges. Obviously, if you're using distributed systems, you'll know what some of them are, but particularly at massive scale, like AWS runs, okay? And there's basically 4 topics. One is like fault isolation and blast radius and how we deal with that at a sort of massive scale of AWS. Some thoughts about like concurrency overload, because everyone has to deal with like spikes in traffic and stuff, and we'll talk a little bit about how to do that well. There's then a concept I find interesting, hopefully you will as well. It's called constant work, and it's the idea that for the really critical systems, and the one I'm going to talk about is Route 53, which is our DNS service, how do you make sure it stays up, basically, and it's it's most critical even compared to all the other things we run. I'll talk a little bit about that, and then just a little bit about how we do health checks and some of the things you can transfer to your own systems there. So let's start with why are distributed systems hard? And I guess some of this is self-evident, some of it isn't. I mean, first of all, you're dealing with unpredictable load, okay? So you've got spikes in load, you've got traffic, you've got things go viral, marketing send out emails in the middle of the night that you weren't expecting, and loads of people start replying, and so on. You've got complex ecosystems where you've got lots of interdependent services, and just almost by sort of science, complexity introduces the risk of a problem. The services you're using are quite specialised, so that means they've all got their own failure modes. Maybe you don't understand them all, because who can? So that's something you need to take into account rather than trying to sort of put your head in the sand about it. You're deploying a lot, so as we saw, you don't wait, you don't avoid Fridays. Quite a lot of you seem to be treating it like any other day. So incremental releases, you're deploying a lot, and obviously at AWS we deploy a lot, like hundreds of times a day. Different channels, it's not just a website anymore, it's all sorts of things, APIs, mobile, etc. And of course, there's no such thing as a maintenance window in most cases anymore. Obviously, if you're in a regulated industry like banking or something, then that's different. And the last bit is, as our CTO says, everything fails all the time, right? So this is kind of tongue-in-cheek, but it really just means it's important to recognise that at a large enough scale, everything's going to fail, whether it's your hard drive, your power, the physical rack, someone will crash into it at some point or break it, whatever, everything fails. So factor that in to the way you design your systems. And basically, as I said, there's 4 different sort of pillars I'm going to talk about: fault isolation, handling overload, doing constant work for critical systems, and then some stuff about observability and health checks. So let's start with fault isolation. If you use the cloud a bit, some of this will be familiar, but I'll start from the top and take it down to the sort of more detailed level. So the first concept that we talk about a lot is this idea of blast radius. And this is the idea that a failure isn't really binary. It's not, it's failed or it hasn't. It's more about some things will be affected, okay? So first of all, who's affected? Secondly, is it all the workloads or just some of them? What is the functionality? Because it might be, a subset of your overall set of operations that fail. And finally, is it, for global systems, where? So is it a global thing, or is it confined to, for example, one country or time zone? And you can design your systems so that you basically pick a blast radius, and it basically contains an error. You might decide it doesn't really matter if the whole thing goes down because it's just for information only, or you might decide that you've got to be really careful and you can choose whereabouts you are on that spectrum from global down to cell level. And the first kind of line of defense, which I guess if you've used AWS you'd be pretty familiar with, is regional isolation. So basically all AWS infrastructure is basically cloned in each of these regions. So we've got about 30 odd now, I think. I'm supposed to know that, but I don't know the exact number. But the one probably you come across most, because it's the default, is US East 1 in North Virginia. We've got Ireland, we've got London, we've got Singapore. And that's basically a fully independent stack. We never deploy a new feature to multiple regions simultaneously. They're always rolled out in sequence. So that's the sort of level of protection. But also, if you're designing your system, you might want to, especially if you've got a global service, you might want to deploy that into different regions, and you have to decide, are they independent or are they sort of codependent? And there's lots of different ways you can do that. And then within a region, and actually a lot of people say, well, do I need regional isolation? In fact, not many people do. You can usually get away with zonal isolation. And what we mean by that is in each region, so it might be London or Oregon or wherever, an availability zone is one or more data centers, often one, but sometimes more. We don't expose like where they are or anything like that, the addresses, but if you drive around some industrial estates in various places, you can probably guess where they are. And each availability zone is basically kind of an independent power, networking, cooling, and everything else. The idea is basically sort of if a plane hits it, others are available. And it's got a kind of fast network that we own. It's not a public network between it. So it's basically an independent failure domain as well. And we manage a lot of that for you. So if you're in a region, some of our services have zonal failover without you even caring. The next level below that, if you sort of want to get down into it, is cell-based architecture. So this is the idea that, and it's not a physical thing, it's a logical thing really. It could be, a cell could be racks, or it could be EC2 instances, or it could be, Lambda functions, I guess. The idea is you spread your load in terms of your customers, whoever it might be, your users, across cells. So if one cell goes down, you're only losing a subset of that customer. And in this case, it's a quarter of them. But even then, you can add more cells, but it's not perfect. So you can go even more fine than that. Quick aside, sorry, I missed this one. So it's not a new concept, cell-based architecture, okay? That's the Titanic. The Titanic was designed so that it would withstand failures in up to 4 of the compartments below the waterline, because they were separated by bulkheads. But unfortunately, it hit an iceberg and 5 compartments failed. So pretty bad luck. It's really just to illustrate the fact that no matter how kind of perfect your architecture is, something's going to fail, and you have to design it with that in mind. And what level of failure are you prepared to tolerate, basically? So that's cell-based, and you can actually do something more that's a kind of variant of cell-based, which is something called shuffle sharding. And that's the idea that if you look on, it's a bit small probably, but on the left-hand side, we've basically got the cell-based architecture I was just talking about, where you've got customers spread across cells, or shards as we call them here. It's the same thing, it's just a logical unit. And in shuffle sharding, you say, well, actually, what I'm going to do is I'm going to put customers A's workload spread across more than one shard. So say A's on 1 and 3, B's on 2 and 4, C's on 1 and 4, D, and those are customers, are on 2 and 3. That means that if one of these goes down, shard 4, it's only affecting 2 of your customers, B and C, and even then they've got kind of other shards available because they've spread their workload around. So as you go down this path, you're decreasing the blast radius every time. And obviously it doesn't have to be 2 shards, it can be thousands, and we'll see an example later on when we talk about Route 53 of where the blast radius, if one cell goes down, is like a trillionth of the overall operation of the service. So there we go. So just to recap, regional, you're basically capping out at sort of 10%, at least 10%. And then if you go right down to the shuffle sharding end of the spectrum, you can get it down to 0.1% if you have a single outage of your customer base or your user base or your system, whatever you want to define, will be lost. And you can't even go lower than that. It just depends how much money you want to spend, basically. So it's about designing it based on the need. So that's fault isolation, and we'll see an example of that later on when I talk about a specific case. The next one is concurrency overload. So what do we mean by that? Concurrency, as opposed to like requests per second, is a point in time measurement. So in that example there, the bars represent the start and end of a request where the system's doing something. And so that dotted line there, you've got a concurrency of 3 because three things are going on. And the reason it's not the same as requests per second is because the duration matters. So resources are consumed in a way that depends on both the number of requests per second, so the amount of traffic coming in, but also the duration. It's called Little's Law. You don't really need to know that, but it is. And the lesson, I suppose, to learn here is that if something causes the duration of your processing to go up because like the system's getting congested for whatever reason it might be, your concurrency goes up automatically. So you might be dealing with the same number of requests per second, but the concurrency can dramatically go up as things start to go wrong. So looking at how that develops, normal service, all your services are fine, all good. Resources are available for new traffic. And then something in a sequence of bits of infrastructure, whether it be, like the traditional tiers of the architecture through front-end compute database, or a more complex kind of event-driven process, somewhere in that chain, something starts to go wrong. And that means even though the traffic's staying the same, the concurrency is starting to go up. And what that means typically, if you've got any kind of queues in your system or any kind of things like that, they'll start to fill up, or you'll run out of threads in thread pools on servers, or you might just start timing out or running out of CPU. And it develops what we call back pressure, because if something downstream starts to go wrong, it's going to push the effect back up the chain until finally we end up with this thing we call congestion collapse, where everything goes wrong. And usually, unless the system has been designed well, that can actually get worse before it gets better, because a lot of systems have automatic retries and things in there, and they're just going to add more load. So you end up with this massive cascade of problems that can take longer to fix even if you switch everything off. So yeah, that just looks at the same thing in a different way really, which is the retry cascade. I mean, I don't know if you know this, but like if you ever use the AWS SDK to make calls to things, it has built-in retry logic in it, and it does it right, which we'll see the right way to do it in a minute. But you can do that naively and end up making things a lot worse. So what can you do about it? Well, firstly, the obvious thing is to just put queues in between the key systems, so that you've got basically a buffer. So if something downstream starts to cause problems, the requests go into a queue, and it basically handles bursts of traffic by filling up the queue, and they do get processed eventually. But it's not a perfect solution, right? Because let's say you've got something properly wrong. That queue is just going to get bigger and bigger and bigger. And as it gets bigger, first of all, the messages that got into the queue first are going to get stale and old and probably irrelevant. But also, the longer the queue, the longer it takes to clear, okay, if you process it at a fixed rate. So you might end up with a situation where the things that put the things in the queue in the first place have long since timed out, and even if you did respond, it's kind of dead work that isn't needed. So again, what can we do about it? Two of the most common techniques are, first of all, cap your queue length. So decide what's clearable in a reasonable time and don't let anything more than that get into it. And when it's full, just reject new messages from getting in it, which gives you a kind of fixed maximum duration for your recovery time. And the other thing that we do quite a lot at AWS is we basically just drop all messages. This idea that I was just talking about, where clients can time out. There's not really much point keeping things that are older than the client timeout. Just discard them and rely on anything that got rejected to retry. Depends on what it's doing, right? Because obviously you've got some things that you can't, like banking, you can't just throw transactions away. But you can have idempotent processes that put things back into the queue. So another way to look at this again is about looking at the response time as your load increases. So the bad case is kind of this, where your load basically goes up and the response time starts to go non-linear as everything gets congested. And if you think about like what the client timeout is, basically once your response time exceeds the client timeout, you're basically not doing anything. Your availability is dropped to zero. Okay, so at that crossover point. And looking at yet another way, we have this thing we talk about in AWS called good put, which is basically useful throughput. Okay, it's not throughput that ends up with an error or just is wasted. It's useful work. And what normally happens without any sort of safeguards in place is that your load increases and your good put increases, but then as soon as things start going wrong and you get this congestion collapse, it drops off. Whereas really what we want is we want it to stay as close to that maximum level as possible in the face of load. Otherwise, we're not doing our job right, basically. So the most common technique we use, and this is actually baked into quite a few of our SDKs and things, is something called a token bucket. And the way this works is it's a rate limiter, and it limits the rate in the following way. So as a request comes in, the rate limiter says, are there any tokens available to me in the bucket? If there are, it processes the request. If there aren't, it rejects it. And that bucket fills up with tokens at a particular rate. Okay, So your request rate can never exceed the rate at which the bucket is being filled, and it means that you can dictate what the maximum request rate is, and beyond that you do what we call load shed, which is just discarding further requests. You give them a decent error message, but you don't allow them beyond that point. And the effect of that is, instead of dropping off to zero good put above a certain load, you can extend your ability to handle a certain load closer to the maximum effective throughput for longer, before eventually, everything will collapse at some point. But it's a good technique to protect your systems with these load shedding things. I guess the hard part is deciding where to put them. We talked a little bit about retries and things like that before. So another thing you can do, the naive approach, is just retry and retry and retry on a timeout. Challenge there is you get things synchronized in such a way that they're all doing it at once, and so you get these spikes of things retrying together. But also, if it's not worked a couple of times, probably there's something more serious wrong. So you can do this thing called exponential backoff, where you basically you retry on increasingly long intervals, so with the assumption that if it's not working now, it might not be working again in a few minutes, and that avoids this problem of cascades. But it still has the problem that things are going to get retried increasingly regularly. So you can do a thing called jitter, which is basically a random variance on the retry intervals, so that they're not all happening at once. And that plus token buckets is actually kind of baked into a lot of our SDK calls under the hood. So if you stick a network monitor on and see what API calls are going through, you will sort of see some of those effects for some of our services. Okay, so defending against overload, you've got queues, you've got load shedding, and you've got backoff and jitter on your retries. The next one is probably something you don't always need, okay? I'll be honest. It's really for the most critical systems, and the one I'm going to give an example of is Route 53, because that's our DNS thing. But basically, it's the idea that the risk of any system kind of failing catastrophically is proportional to, well, first of all, how often it's changing, and secondly, just generally what's going on in terms of states and things like that varying. And the idea of constant work is you basically do the same amount of work all the time, even if the load is low, as you would do if it's under very high load. So you're basically deciding what your peak load is and running it as if there was a peak load all the time. And I'll show you a little bit about how that works. And the other principle that goes alongside that is this idea of anti-fragility. So this is basically, if it's under stress, it's more likely to succeed. So you have like a core of the service that will always continue to operate, even if the things around it that are the good things to have, but not completely critical, start to fail. And the example I wanted to talk about is Route 53, which is our DNS service. We actually don't advertise this, but it does have a 100% SLA on the data plane. So if you don't know what data and the concepts we have are data plane and control plane. So the data plane for Route 53 is just you want to resolve a DNS entry. The control plane is the APIs that do things like I want to add a new entry or I want to change an entry. And it's the same with all our systems like EC2. The data plane is can I SSH into my EC2 instance? The control plane is can I add a new EC2 instance or change the AMI or whatever. So because we want to, everything basically depends on DNS, even internally, so it really needs to work well. And so we apply pretty much all the principles I've talked about so far into Route 53. You've got regional, zonal, cellular, and shuffle sharded design. And the output of that is the blast radius of one of those shuffle sharded cells going wrong is basically a trillionth of the overall service capacity. So, it costs a lot of money, believe me, but it is pretty reliable, and it's actually never gone down, although, you might have remembered something that happened in October last year. And if anyone wants to talk about that later, I can, because it wasn't Route 53's fault. So, layered protection. Control plane on the left, data plane on the right. So API calls to do things like add DNS entries or change them come in on the left. DNS requests resolve this DNS entry coming on the right. Okay, and we have bits in between that I'm going to talk about. So the first thing we have is what we call a poison taster. So it's basically a mini version of the entire system. If an API call comes in and says, I want to make this change, we check whether it will put this whole system into a bad state. And if it will, we just completely reject that. So it might be a malicious request, or it might be something that's just, it's not just validation, right? It's flushing it through the whole system and seeing what the end result is. Then there's constant work, like we were talking about earlier. So here, this config server kind of reconciles all those API requests coming in against the current state, and says, right, what's the new end state based on all that? And it will then write it to a massive S3 bucket, but it won't just do the changes, it will do the whole thing every time. So that means that even if you got like no requests coming in, on a heartbeat, it will be writing that entire thing out every time. So it doesn't matter whether they're all new or they're all the same, it's still doing the work, which means there's less changes going on and it's less likely to crash. The next principle is about the data plane being simpler than the control plane. So a lot of our systems, if the control plane goes down, we can keep the data plane running. And the way we do that in this case is the config that goes into the actual final place it's used is pulled rather than pushed from that S3 bucket, because we found over the years that if you push things, it's more likely to overwhelm the destination than if the destination pulls things from its source. And another thing, sort of variant on that, is having fewer things pushing to, if you have to push, having fewer things pushing to a large number of things is also safer. Okay, so everything every time is constant work. And then the last kind of line of defense, if everything goes down, the control plane goes down, the config pusher and puller go down, ultimately you've still just got a massive DNS table in memory spread across loads of machines. And we even do things like killing, logging and monitoring and health checks before we kill the service. So far, fingers crossed, it's never gone down, because it's designed to have all these layers protecting it. Okay, so just to recap, keep it simple, don't have different modes, we didn't really talk about that, but constant work, and make sure you know what you're going to sacrifice first. And there's actually a follow-on to that in this little section, which is about health checks. So first of all, how we do health checks at AWS. And by the way, health checks is like the first thing you do. Sorry, I just put a timer on there. I'm out of time. So first of all, it's just liveness, and that's local. And it's like, you know, can you connect via TCP, or can you ping it? It has low false positives, okay, but it's also not very sophisticated. So then we do a broader local health check, which would be, is the service as a whole in, you know, this boundary that we define working? So it might be, have we run out of memory, a CPU, disk space, those sorts of things. And again, it's pretty good, but it misses dependency failures, and most of our systems have a lot of dependencies. So the third one is the dependency check, and that's more about, you know, can you see the database that you're connecting to? Is your cache still valid? You know, what's the cache hit rate and so on? And things like, are your downstream APIs working? And that's much better, but it's still not perfect. So the last thing we do is anomaly detection, because we found on these systems where we're running lots of different things that outliers tend to indicate there's something wrong. So if the service as a whole, if 99 of your servers are all you know, hitting a particular rate of success, but one of them's much lower, there's a good sign that something's wrong there. And we usually kind of raise alarms, and it's got a very good detection probability, but it's also very complex. So you have to be a little bit careful about, it can cause false alarms a lot. And obviously in the worst case, that gets people out of bed. So it's really having a mix of all these at different levels, and learning your system and how it behaves over time so that you've effectively tuned the sensitivity of each of these health checks. And I said at the start about health checks being the most important thing. It's really true. It's like a bit like test-driven development. Write your test first. We say that it's best to prioritize the health check before you actually kind of write the code. So never say, "Oh, I didn't have time to do the health check," and also devote enough resources to it. So generally, we have a lower margin of error on our actual service than we do for health checking, because if the health check fails, you're effectively flying blind. We talked about those different layers. Centralized decision making is something that's been done for years, but it's getting easier now. I deliberately avoided talking about AI tonight because I'm sure everyone's a bit sick of it. Certainly I am. But actually, language models are pretty good at doing this anomaly detection and figuring out the outliers. And so are, more straightforward classifiers that have been around much longer. So centralizing that decision making so you can say, well, that one might be working, but what about the other ones is very important. And finally, this balance, thoroughness versus false positives. You can really, you can over-engineer these and have false alarms going off all the time. So really, it's a question of build it, stick it into action and see how it performs, and then tune your settings so that you've got the right level of response. Okay, so just to wrap up then, distributed systems are hard to manage for various reasons we talked about around complexity, and we have learned a lot over the 20 years we've been doing this. So the 4 key things, if you take nothing else away, are fault isolation and picking your blast radius to be appropriate. Design not just for your normal load, but for overload and how you're going to handle those to avoid congestion collapse. If you've got really critical things, think about doing constant work, and really don't shortchange your health checks. They're not optional. They need to work well. And although we're not suggesting anyone should invest the amount it costs to run Route 53, some of these principles are applicable at every scale. So hopefully there's something you can take away there. And rather than try and remember everything I've said, we have got something called the AWS Builders Library where quite a lot of this content comes from. It's not very well advertised, so I've got a link to it there. But basically, it's rather than me, who doesn't actually build these systems, I just talk about them. These are the sort of really senior people who've been doing it for ages, who've written articles about how they run particular systems and the lessons they've learned. It's a really good read, actually. It's something that, the privilege I have, I suppose, is being able to talk to these people who are running these systems that serve trillions of requests every day. And it's great to learn from people who know more than you, basically. So I'll give you a minute to just grab that one. And then last but not least, if you wouldn't mind, feel like it, no obligation, just we've got a little survey so that we can learn for next time. Thanks very much. Are we doing questions, chaps? Yeah, questions.
Any questions? Yeah, I guess so. You see a lot of people saying, if you've only got a few users, don't plan to scale them because it's a waste of time. Wait until you get the scale. Where do you stand on that? Can you just repeat the question?
Oh yeah. So the question was, if you don't think you're going to get loads of new users, your user base is pretty constant, should you plan to scale? I guess I'll give a consultant's answer. It depends. I mean, I'd say more often than not, yes, because there are quite a few things you can do that don't really cost anything. The opposite end of the scale is, a non-critical service that only works during office hours and isn't going to kill the business off if it's not working for a couple of hours. And then I've had conversations with people saying, do we need regional failover for that? And that costs a lot of money, right? So you don't need that, right? You just have a disaster recovery plan where you can spin up some new servers or something, and people will have a system that's down for a couple of hours. It certainly won't be worse than it was back in, if you're running it on premise in a data center. So don't go mad. But for example, you could say, well, actually, I'll run it on Kubernetes, and then I can scale out a little bit on pods and things. Or you could say, well, I'll hand that problem to AWS and use Lambda functions. If it's just like a little bit of code behind an API, then a Lambda function is a good fit, because if your traffic increases, it'll scale automatically, and we'll just do that for you, basically, within some constraints. Usually it's something like the database that's the hard one to do, actually. Yeah. Does that answer your question? Yeah. Any more?
You're talking about health checks and not letting individual instances decide they're unhealthy and doing that aggregate. That sounds interesting. I'd love to hear a little bit more about that and how you see that working.
Yeah, so you talking about the anomaly detection, or?
No, one of your slides just had a thing about health checks don't let individual instances decide they're unhealthy.
Right.
Aggregate it.
Yeah. So the question was, talk a little bit more about how you go beyond just what's the health of a specific instance and what's the aggregate of that. It's important to know each individual instance does know what's going on, right? So that is definitely one signal. And then there's like layers you can aggregate those up. So simple ones would be what percentage of our instances are up, right? Based on pings and things like that. But then you get another level above that, which is about, well, set a band, say, this is our operating window. All the parameters should be between these levels, right? And if we get more than 2% of our instances going outside that window, that's counted as an anomaly. So that's a reason to sort of raise a Sev 3 or something. And someone will look at it then and say, oh no, it's fine. It's just that those ones have got a bit like they're having a bad day or whatever. But it could be the early signs of a bigger outage. So it could be something that's creeping through the service as a whole because something's gone wrong. So, I mean, when we have outages, typically it's a deployment change, right, that causes it. And you get a situation where a deployment change is rolled out. You start with like 2% of the entire estate, and then if that goes okay, you do 5, 10, and you roll it out progressively. So sometimes those problems propagate in a predictable way, and we can build tests that look for those as well. Yeah.
Just on, like most of this stuff makes perfect sense. You can see how it's applied. One thing that I'm kind of struggling with was the constant work and how that works in practice, because it makes perfect sense for Route 53 because of the criticality. Don't see how it applies elsewhere because of the sacrifice that you have to make cost.
Yeah, I mean, it would be, if you're building like, the places we'd see it, I guess, are kind of very high levels of throughput transaction processing systems at banks and stuff like that. You know, things that would have run on mainframes and probably still do in a lot of cases, yeah.
Yes.
You know, because they're just really good at that. Like airline booking systems and stuff like that. And, you know, if they're not actually doing the constant work, so that in that case, Route 53 was writing the entire thing every time. It might be a sort of lighter version of that, is just have it over provisioning capacity for your worst case scenario at all times. That can cost a lot, but is worth doing, I think, as well. Yeah.
What do you think of multi-cloud strategy for resiliency?
Okay, so the question was, what do we think of multi-cloud strategy for resiliency? I guess it depends what you're doing it for, right? I would say the number of times we see it really being needed is quite rare. We actually changed our advice about a year ago. We always used to say, don't bother, but actually it gets asked so often. I would say the most common use case is like transaction processing systems where you can't lose any data. You want do you know what I mean when I say recovery time, RTO and RPO? Recovery point objective is how far back in time or how far back in your transaction log you're prepared to go and lose things. If it's 0, then there's a case for certainly regional failover. Multi-cloud is really hard, okay, because there are very few services on any of the clouds that are kind of similar enough to make it as simple as just failing over. And there's a risk that you introduce more complexity in the failover taking account of the differences than you would have if you just stuck on one cloud. And I don't think any of the clouds have had a global outage where everything's gone down. But there are some use cases where it's worth pursuing. And like I'd say, I've got a colleague who basically flies around the world and just talks to banks all the time about this. And he says like he's seen 3 banks who've implemented it effectively. So it's really a niche thing. But you can do it, you know, it's just hard and expensive. Yeah.
Thank you for the brilliant talk. It was really good. I was just wondering, you alluded earlier to about the kind of broad scale AWS advantage on DynamoDB that goes in on the, which is, I'm not too worried about like what the attributes and that were, but I was wondering whether any of these strategies or other change management strategies could have helped either stop that from occurring, or what changes were made in the process of that happening in order for it not to happen again?
Yeah, so great question. The question was the October 2025 outage. Were there any lessons we learned from that? Absolutely. So I'm not saying we're perfect, but we have this principle of if there's a big outage, we run a process called correction of error, and we publish those correction of errors. And actually internally we use them a lot more, like hundreds of times more. Basically, if anything unexpected happens, the person who was, although there's a no blame culture, the person responsible has to write a correction of error document and present it. And we also have a weekly ops meeting for the whole of AWS. You don't have to go, but anyone can go. And it's got like various like VPs in it and stuff. And every week they do the review all the COEs. It takes like two or 3 hours. But what we did in that case, so it was quite a hard to predict thing. It was DynamoDB using Route 53 for DNS, right? So it wasn't DNS. DNS was fine. It was the way DynamoDB was managing its DNS set. And there was a race condition between, there were basically 2 writers that sort of flipped. And for reasons we are not sharing, one of them took an unanticipatedly long time to do it, so that the second one then stepped in, and for details I can't share, it basically wiped the entire thing because it overwrote with a stale set of DNS entries, and there was a kind of recovery daemon that said, hang on, they're out of order, I need to wipe that because it's stale, and it ended up with nothing in DynamoDB's DNS entry. The recovery was quite quick on actual DynamoDB. It's maybe a couple of hours. They just manually restored it to last known good state. But what took like I think 14 hours was, and again this is the thing of like these complex systems having so many dependencies. DynamoDB is used by loads of other services to just store the intent of the control plane. So it acts as the queue basically for, say you autoscale, you've got a load of EC2 instances or a Kubernetes cluster and you want to scale out. That just says to the EC2 control plane, go and get me some more instances. And those messages come through the API and then go into a DynamoDB table. And another thing reads those and says, all right, this guy wants another EC2 instance. But it didn't know where to, it couldn't do that because it couldn't resolve DNS. So it was just all messed up. So the lesson was spend more time thinking about the edge cases, you know, and the solution was there's no longer 2 things writing that, there's only one because it will then, it might be stale, but at least it will work. Yeah. How are we doing for time? Last question, folks. Yeah, you've had your hand up. Yeah, go.
So would you rather manage EC2 forever or go serverless?
I mean, personally, so I'll tell you what I did when I had my own startups. I had Kubernetes because we were quite a small team. I got sick of managing it. So I did go serverless for one thing, but then what it was doing was not super complex. We had very few long running processes. It was all just like, you know, API calls, pulling stuff out of persistent data stores. So for that, I think Lambda's absolutely great. And you can get up and running very quickly with Lambda. But, you know, it depends how big your team is and what you know already. What you know already is useful because you can be very productive with what you know already. But I'd say if you're starting from scratch, always look at serverless, really. Yeah. Okay. Thanks, folks.